All right. Started.
Hello, everyone. Welcome to today's session. So we went over linear regression in last class. We'll start with a very quick overview by Vidya on the homework that we did on linear regression, and then she'll also quickly do a status update on where we are in the Idli Dosa Vada assignment. So that's where we are right now. Over to you, Vidya.
Yeah. So can you see my screen now?
Yes. Yeah, we can.
Yeah. So this is a linear. So the homework assignment was to find the loan amount. I mean the amount column here using the linear regression. So we have the loan data here, which has amount, interest rates, grade of the credit. I mean that's the credit score. I think credit grade of the customer, years of their employment, ownership, income, age, and for this data we have dropped the value default, which is either 0 or 1, and I proceeded with only the other columns. So this is the basic loan info, and I checked for any basic EDA actually, like whether it has any missing values. And then before I began, I just wanted to see the correlation between different variables, that is amount and because this is what we want to predict, the loan amount that we want to predict. So and its correlation with interest, years, income, and age. So it seems that there is not a very positive correlation between them. Very positive correlation between them. The trend line is just like close to a horizontal line. So we can see for amount versus interest, amount versus years, and amount versus income, amount versus age, and all these. So next we plotted a correlation matrix to see the correlation between the variables, and it seems like only the income the amount has the highest, like 0.32 correlation, a positive correlation of 0.32, and others all didn't have a very significant positive correlation here, and certain had negative correlation. And when we proceeded without standardizing or normalizing our data to, so it was the mean squared error was around 32 million. That was so high. So we had to proceed with, after I proceeded after standardizing the data, uh, and um, and this is how the numerical columns looked like after standardization. And I didn't do any standardization to the grade and ownership. I kept it as such, and moved it to a one hot encoding the grade and ownership. So basically the one hot encoding is we could see the grades from A to G, and what it does is it transfers the grade into columns. As you can see here, there are grade A, B, C, D, and E, and for corresponding data points here, if the grade is B, then it gives a value 1, and for others it gives value 0. And this is what one hot encoding does. And the same has been applied to ownership status also. And the numerical values are standardized here. And then we proceeded to
Question. Is there a need
yes.
to standardize numerical values?
I guess yes, we see, because I before using any machine learning models, or I guess it's very much important that we standardize the data, so that there are it only ranges between a certain value. So so I think yes,
Bhargav,
because
does linear regression,
You see,
is there
sorry, question is like, what is standardization?
oh, okay. So basically you just make sure that if you look at amounts, can you go to the file, Vidya? Open the file.
yeah.
So if you look at amounts, it ranges from, say, zero, oh, not
5,000.
zero. Yeah, 5,000 to
5,000
say
to 35,000.
35,000. Then you have interest rates, which probably ranges from say 5 to 13. Years maybe from 10 to 100 or 50 or whatever, right? So if you look at it, the units are very different, and you're trying to put all of them into a single equation. Of course, in this particular case, you have amount is your dependent variable because that's what you're trying to predict, and the rest are what is called as independent variables. So the whole idea of standardization is to make sure that in terms of units, they're all in the same units. Now, how do you go about standardizing? So the easiest way to standardize is, again, goes back to, again, by the way, folks, anything and everything we do here is all class 11 and class 12 math. Most of us don't realize it, but it's that. So the way to standardize this is, if you go back to class 12 math, you would have learned normal distribution. And so there is a standard way of, so if you have a normal distribution with mean mu and standard deviation sigma, if you remember, you can standardize the normal distribution using the z variable, where z is equal to x minus mu by sigma, where x, so if you, for example, let's say hypothetically, if years were to be assumed to be a normal distribution or distributed normally, then you calculate the mean, you calculate the standard deviation, and then every data point is standardized. And the way to standardize it is, in this particular case, would be you take the data point. So if it's 10, you take 10 minus mu, which is the mean of the years, and divided by the sigma, which is the standard deviation. Now, when you do that, what happens is everything becomes standardized. So if you look at the standard normal distribution, so if you can recollect, you would have the mean as 0, the standard deviation is 1, and then you can probably go to maybe 3 points to the right, 3 points to the left. When I say 3 points to the left, I mean -3, and then you kind of hit the tail, right? So everything is standardized, everything is in the same units, becomes easier for comparison. So that's the whole idea of standardization. Is that clear?
Yeah, clear, VC, clear, yes.
But
Thank
my question is, when we are doing regression, linear regression, and assuming that all these are numerical variables, for the sake of discussion, let's take ownership and grade out of the picture. Do we need to do standardization, Bhargav? I just wanted to know that.
Yes, so we need to do. The reason is, for the reason you told, the units have to be at the same time. So, okay, let's assume, so what is the objective function that we are trying to minimize? The objective function we learned last time, the parabola. It's the mean square error, right? We're going to minimize mean square error. And when we want to minimize mean square error, we're going to take partial derivatives on every single variable that we have, and that could be for every single feature that's out there. It's for interest, for years, for age, for every single thing. If they are not in the same unit, then the way your derivative, your gradient would go is that for some, say for example, age will always be between 0 and 100. For a loan applicant, it's probably going to be between 21 to say 70, right? It's going to be, that's all the range is going to be. A much narrower range compared to say a salary, which can be anywhere, say between say 3 lakhs to a crore, as an example. Now that spread is so high that even for small changes, your gradient would always tell you to go and then optimize more on salary and not on age. So if you build the same model without standardizing, you will get a different result where your features, all the other weights are going to change very little or going to be so small, and there's going to be enormous amount of weightage provided only to the one which has the highest magnitude that's out there. So we're going to take the magnitude out of the equation and ensure that everything is within the same range, and then going to build a model. So that's one of the this primarily came from the world of statistics, where we assume that any variable that we are going to use in the model are independent to each other.
But question, Bhargav, so when we are standardizing here, I mean, we are used to subtracting the mean of the data and then dividing it by the standard deviation. So is that how it's usually done always?
No, that's not. Yeah, good question. So that's not the. So over time, we have understood a whole bunch of. Okay, so let's start thinking about why that's actually a brilliant question, and it's not a with a non-trivial answer. Okay, so question for anyone who's out there, particularly someone from computer science background. Is everyone used to understanding what the big O notation is in algorithm?
Yeah.
Complexity.
Time complexity.
Yeah, time space complexity. Is that something that like I can, or should I try and answer without telling that? Okay, maybe most of you don't understand it, I guess. Okay, because like literally two-head that went like this. So, okay. So what happens is that if you have like 10 million data points, right? If you have 10 million data points and I want to find mean and standard deviation and then subtract mean and standard deviation for all of it, takes a lot more operations than some other kinds of standardization that I can do. A simple standardization that I can do is called min-max scalar. What it does is that I'm going to take my value and then subtract it to the minimum value that I see in my data set divided by max minus min. That's called max min scalar, right? Very common thing. So standardization, normalization is one way to do, but I can also do min max scalar. So there have been, and this is like extremely efficient compared to say doing the standardization using standard normal standardization. And at large amounts of data sets, the performance are equal, or sometimes even min-max scalar outperforms all of this. So a lot of times it all evolved through the necessity of computational power. But having said this, in this day and age, for the kind of data set that you're going to work on linear regression, it doesn't matter as long as you can put it in a very bound range, and all of it follow a very similar bound range. It can be normal min-max scalar. There's also a normalizer function. There are like a few standardization functions that if you use any one of them, but you need to use one of them.
So question. So let's say we're doing that, all right? We're doing that to amount, interest, years, income, and age. Sorry, Vidya, can you continue to share? I'm not able to. Yeah, thank you. So if you look at some of these data points, for example, negative 1.1376, now that's certainly, it falls below the mean. Not a freak value, but certainly leaning towards, and maybe years has a better example, 2.86. So that's certainly relative to what we have. It's a freak value, correct?
Correct.
Now, question is, so we have these ordinal, nominal variables. Let's say it's a nominal variable, not even ordinal. How do you even go about standardizing take ownership as an example here?
You wouldn't run standardization on. Okay, so let's start with the basic premise of what we're trying to do. We want them in the same unit, right? For categorical variables, you will not go and do it. Okay. So nominal, ordinal, you wouldn't do it.
So would you exclude it from the regression?
It'll be excluded from standardization. Your standardization would be only applied on like the way she has done. I think she's done it correctly. She has standardized only amount, interest, years, income, age,
right,
and not on grade and ownership.
Right. Okay. So the question here is, so when the regression happens here, so does it treat as though there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 15 variables. Is that so?
Correct. That is correct. Yeah, she's correct. That's right. Yeah. Yeah. You use all of it. Now, it's a good segue into it. May I share my screen?
Yeah.
Let's take this example of wait 1 second. Okay, this is grade. Okay, A, B, A, C, A, B, D. Let's say this is what we have, right? Now let's start talking. So this is like, so now we need to encode it, right? We need to, now encoding, there are two options to do encoding. One is called label encoding, where we go and then tell that when I see A, I'm going to give 1. And when I see B, it's going to be 2, 3, no, A is 1, B is 3, A is 1, B is 2, B is 4. This kind of encoding where for every unique value, I'm going to give a number. And then when I encounter a new thing, I'm going to increment it and give it. This is called label encoding. Some reason this is like, okay. This is what it is. The other, so this is what is called label encoding. The other one that what Vidya has done, it's called one-hot encoding. The way it works is that for every unique value, so quick pop quiz for all of you. Unique value in a set, what is it called? Number of unique values in a set as a specific term. You have a set, and I want to find the number of unique values in the set.
Set
Yes,
will have only unique values, right?
Wait, what?
Set contains only unique values, right?
No, yeah, like, yeah, number
So
of
cardinality will give the
cardinality. Correct, that is the word. Cardinality. Good. Cardinality means that in a set, the number of unique values is called the cardinality of the set. So cardinality here is 4.
Oh,
right? So I have only 4. For every unique value that's out there, I'm going to create a column, right? So
something like grade A, grade B, grade C, grade D, right?
correct, correct. And then B, C, D. And then when the way it works is that we don't need this. Now, when there is A, it is going to tell 1. And there is B, there is no A here, right? So this is 0. When there is A, this is 1. When there is C, it is 0. So whenever the presence of A, it is going to tell. Similarly for B, when B is there, it will tell 1, otherwise it is 0. That is how one-hot encoding works. One-hot tells that in my original column, if that particular cardinality, if that's the value I see, then it is 1. If it's not, then it's 0. Everything else is 0. Okay, which means that when I do it, the sum of all of it will be 1. Right? So there's only only one in this particular column that's out there. In this particular row that's out there, only one of the 4 would be 1. Everything else will be 0. And that matches to what it is. So this is called one-hot encoding. Now there are a couple of different ways in which you can think about it. One is if I have only 4, then 1, 2, 3, 4. So for example, if I know that it's ordinal, we know that it means that there is an order in which how my data is, and there is ordinal encoding works, right? Label encoding works. But when I don't know if it is nominal, then label encoding does not work because there is no order in it. So you would use one hot encoding. In linear regression, it is highly recommended. I mean, you have to use only one hot encoding, because the moment you use 1, 2, 3, 4, unfortunately, even if it is ordinal, what happens is it assumes that 2 is greater than 1 by 1, 3 is greater than 2 by 1, which is not always true. Grade A, B, C, D, B is not greater than A by 1. Then we would have done it like this. No. So when you use linear regression, and what we'll cover today, logistic regression, it's highly recommended that you use only one hot encoding. We'll introduce a new class of models on Monday, tree-based models, and there it doesn't matter. It can be either one of it. Now one of the bigger challenges, I'm going to replace one column with another column in label encoding. On the other hand, if I'm going to use one hot encoding, I'm going to replace one column with the number of cardinality that's out there, and that many number of columns increase, right? So it can so happen that I can have, say, 10,000 data points, and that might be enough to build a model. But say that there are 3 columns with each one of them having 2,000 cardinality, suddenly number of columns is significantly more than number of rows that's out there. It's a common problem that you're all going to face when you're working. So remember that it's going to cause problem, and we'll start talking about we'll at some point in the course we'll think about what it means, and one of the common ways to do is dimensionality reduction. When we start thinking about unsupervised learning, you remember we're still in supervised learning. There is a concept of unsupervised learning which we have not talked about so far, which we'll cover many weeks from now. We'll talk about how in this particular context, when your dimensionality explodes, how do we find a better representation of? We'll come back to this point. Remember it and then remind me when we get to it. But that's a practical use case of when unsupervised learning would be used. As like what we have learned is always going to be used in a context. Unsupervised learning will be used as an input to build a supervised model sometime later in the session, in the course. Okay, so label encoding is one way where you can do. One hot encoding is you're going to convert every single column value that's out there in their own specific columns, and then go and build it out. So that's where these are the 2 standard ways in which encoding happens. It all has trade-offs, but in linear regression, logistic regression, you're highly recommended to use one hot encoding, which is what Vidya did. She did correctly.
Question. Can you?
Done. Yes.
Can you show me the? Yeah. So let's say this column, the second column, let's say that were to be, instead of encoding, let's say that were to be, say, age, all right? And against the first row, you see a -3. Against, just replace the encoding column with age. Age. Yeah, just call that age. Right. So the first row, you see a -3 and the -2. Okay. So instead of 1, yeah, you see a -3 and then a -2 and then maybe a 3. So basically, let's say you've normalized you've converted the data into standard normal. Okay. Of course, we won't see a 4. I don't expect to see a 4, but maybe freak possibility, whatever. Now, this is the range in which you're dealing with data as far as age is concerned. And any numerical value, that's the range in which you would typically deal after doing the conversion to standard normal, or rather after normalizing from a user term or standardization. But if you look at columns, grade A, grade B, grade C, grade D, you're never going to see that kind of range. You're just going to see a 1 and a 0. My question is, does that impact? I mean, when we do regression, what matters? Does the variability within a column matters? Or because on one hand, you have standardized the rest of the variables or rest of the features in this case, and they all range between, say, a -3 to +3, let's say, okay, typically, unless there are some very freak values. On the other hand, you have a bunch of columns. It could be many for that matter, which the regression model will treat as numeric. It's not going to treat it as something else. It is going to treat one as though it is one, right?
Yes.
So
Correct.
I'm just trying to understand. Yes, we have converted that into a numeric, but what is the implication? On one hand, we have a -3 to 3, and then you have plethora of columns which are just ones and zeros.
So you're telling that the range is higher here and the range
Correct,
is
correct.
lower,
Doesn't
right?
that come back to the original problem where we had an amount
But
where the
if you
range was huge?
Fair point. Okay, good point. But one thing to remember this is that this number is still bounded. It is not an order of magnitude higher, right?
Agree.
So we'll assume that at this point in time, the model will be able to learn because we're randomly initializing. We're going to run at a few iterations, and then it's going to pick it up. And to your specific question, that is this going to impact, like am I getting messed up or not, are things that will start. We haven't discussed how validation works yet, right? We'll give it some time. I'll cover it today. Like we'll do logistic regression. We'll come back to that's the last topic for today, where we'll start thinking about how do we pick model, how do good features look like, how do bad features look like, what things to look for. There's a very specific term called overfitting, which is super important for you all to know before we move to tree-based models. So those are all the things that we'll cover. We'll come back to we'll cover a bit more and then we'll come back to it.
Okay, all right.
Okay, good question. But the TLDRs, it won't affect. It's generally okay.
Okay.
Vidya, over to you.
Yeah. So this is the one hot encoding that we have done here. So and we'll proceed to train the model using the train the model by linear regression, using linear regression, and we have seen that the mean squared error is around 0.84, and the R square is 0.15, which for example, like the mean square error without standardization was around 35 million. So that was quite high. So after standardization, we could see a significant decrease in the mean square error. So I think the standardization is important for before we proceed using any machine learning
Question:
model.
does MSE even matter in this case? Because it's only a question of scale, isn't it? Because the numbers were huge, the amounts were huge, which is why MSE was huge when you didn't standardize it, right? But now that you have standardized it, of course, it'll be smaller. Don't you think that what matters much more is R square?
Oh, right. Yeah, I didn't think about on that way.
Right? It's merely a question of you're dealing with smaller numbers, so MSE will be smaller, right?
Yeah, right.
Correct? So what matters is R square, because R square
square.
explains how much of the variance in Y is explained by the regression, right?
Right.
Which is why R square is very important.
Right. Yeah, but here the R square is also significantly
That's right.
very low.
No, I agree. That's where the problem is. MSE is not the problem, according to me.
Oh, right.
Right?
That's
It's R square. Yeah, it's R square which
because
is
in the
troublesome.
discussion, in the discussion we had, the MSC rate was so
That
high.
is right.
So
correct. That was
yeah,
because
that's
of the
why
amounts. The amounts.
yeah, that's right.
So
That's
huge.
perfectly right.
Right.
Yeah. That's how
Okay,
I think.
Quick question: what does R square mean?
Okay.
Standard state mean value minus fit value divided by standard state mean.
Yeah, I don't want formula. Even I don't know the formula. Let's think about what it means. Like I saw the discussion on the channel also. what does, like, what represent, what is the, like, how would you explain, like, what does an R square mean? This is super important. This is the reason why I picked up this problem to talk. It's in continuation to one of the topics we discussed last week. So tell me, what is R square?
So I think that's the variance
That's the variance.
variance between the dependent and independent variables. And just to look into the details still. I didn't go through much, but
Okay. Anyone else?
It's a guess. I don't know, but is it a because we are actually running some kind of a regression or something, and we are trying to find out the correlation. Is it a coefficient of correlation something?
Coefficient of correlation. Okay.
So how well these two things have been correlated?
But there is not correlation is different between 2 points. Now we have like many features and then one column. So what is the equivalent of it?
Okay. Sorry.
Bhargav, I'll try to tell, but I don't know that I'm sure. So I agree with what Abhinav told. Like formula-wise, that is right. But what it actually means is we are trying to bring in a line where we are computing a mean of each and every point. And what we are seeing is we are checking whether the sum of squared error is greater than the mean or lesser than the mean. Like we are keeping mean as a point. We are comparing on top of that. The formula is mean minus sum of squared error divided by mean. Let's say from each point to mean, we are calculating what is the squared error minus our predictor line from which we are calculating the squared error divided by the mean squared error. When we do this, for an example, if our fit or like whatever the model we came up with, if the sum of the squared error is 0, like if it is close to 0, then R value will be 1. The reason is mean and numerator or denominator will cancel out. If it is large, let's say if it is 0, we'll say it is similar to the mean, which means the predictor line is same as the mean. If it is lesser than the mean, then we are telling it is worst. It is not even close to the mean.
Maybe from what Naveen says, I
I
understand.
can tell you that I don't know, 50 people, there are 18 people have zoned out. Good job, Naveen.
Yeah, I know, but I cannot tell it in a way that everyone can understand.
Yeah.
Okay.
So what I understand is so now when we are actually trying to create a model, so then we are saying is like how accurate this particular model is with the new data. So then if you are saying it is actually either 0 or 1, I'm not very sure which says is like it is 100% accurate and it is 0% accurate. So I think this value represents that.
Vijay, what's your answer?
Okay, I'm taking a guess again. In a crude way, if I have a dependent variable and I think the best guess is the mean. So if you give me data and if you want me to make a prediction, so let's say I have the math scores of a class, and you give me the bunch of data points. And if you want me to make a prediction, then my first prediction would be the mean, right? I would say maybe in the next quiz, this would be the mean would be the score that somebody might get. That's the most crude way of making a prediction. I think the idea of R square, the whole idea of regression is to improvise on that. If I can't even get better than, if regression can't better than predicting what I can do in a crude way, which is just take the mean and say, and show that as a predicted number, then I failed in doing a proper regression. I forgot the math that is involved, but this is what I faintly remember about R square. I don't.
Yeah,
I
I
don't.
think.
Bhargav,
Uh,
Sorry, Bhargav. Go ahead.
yeah, someone was. Yeah, Abhinav, go ahead.
Abhinav.
Actually, what according to my intuition, for in 2 dimension we have correlation coefficient, but for in multi-dimension, what is the change in the future with respect to the change in the attributes is what R square tells. That's according to my understanding.
So okay, no, like you, we see, and Naveen are telling the same thing. It's not like different languages of the same thing, but you see the challenge. But there is an intuition that's missing here.
According to me, I think like it is the difference between the, I mean, the value which is predicted to the actual value.
That is okay. Let's okay. Let me give a different perspective here. Okay. Vijay, you saw the value. You love the MSc, right? The MSc is awesome. It's really awesome. But the R square is terrible. Do you agree to both of it?
Mean squared error. So I'm just trying to understand. So mean squared error would be y minus y hat, assuming y hat is a predicted value.
Whole square, right?
Whole square and divide by the number of data points, correct? Is that right?
Correct, by the data points, correct. And this is what it is. So we are only off. And here, what is the prediction? We are predicting the amount. So amount is not standardized, right? Or amount is standardized, I don't know.
No, it is.
It is, but okay, whatever. This number is a reasonably good number. R square is bad. What does it mean?
I think the regression hasn't been able to explain the variance in the amount.
Okay.
I mean, that's
a very statistical way of.
I know. Very statistical.
Machine learning. Yeah. No. Your answer is correct. Your answer is actually correct. That's what I was looking for, but that's math.
I know, very statistical. I understand. I'm not.
Machine learning way of thinking about it. The machine learning way I told you is like from the quiver. What do we take? What is there in the quiver? It is a hypothesis set, right? In the hypothesis set, remember we talked about it. I'm taking my arrow. The arrow we took is a linear regression, and then I'm doing it, right? Linear regression is a wrong choice for this particular data set because we are telling R square is a measure of the degree of the line. Telling degree coffee, so it's like that. The degree of how good or awesome. No, I went low to test. So how awesome or bad the line is. So if an R square closer to 1 tells that exactly what VC tells. VC made the right definition, is that it's able to explain the variance of my entire data using a straight line. When an R square is closer to 0, the hypothesis that it's a straight line is wrong because it's not able to even remotely explain the variance. So that's all it is. So this is one way where you can evaluate if the hypothesis set that you're using for this particular data set is correct or not. And a 0.15 is so bad that it's not something that you would be useful for you, right? Okay.
Bhargav, hello? Can you please come again with your last sentence?
So R square tells, like my hypothesis is that it's a straight line. How much, is it really a straight line? How much of my deviance is it from a straight line? How much of my variance is this explaining? That's what R square tells. So a 0.15, closer to 1 is good. Closer to 0 is bad. Because closer to 0 means that as linear regression, a linear line is unable to explain how my target moves with respect to features. So it's not a good model. Okay, this is not the only measure that we will use. We'll do a more generic version very soon, but because we want a measure, we want to be able to understand how a linear regression compares to a random forest, and we need to do then apple for apple comparison. R square is defined only for linear regression. It's not defined for other kinds of models. So we need to do something, right? Vijay has
No, just to put it in simple mathematical terms.
yeah. So it just tells that you need to have a value that's closer to 1. Okay. Okay, we'll continue. Okay.
One more question.
Yeah.
So when you said line, right? So whenever we are actually trying to do a regression and trying to fit a model, so are we assuming that it will be a straight line? Or it is
So line is only defined in 2 dimension. Here in 3 dimension it is called a what?
Plane.
3 dimension it is called plane, and 4 dimension and above it's called
Hyperplane.
hyperplane. Correct. So it's called a hyperplane. So we are fitting what is called a hyperplane. Okay. Hyperplane, the definition of hyperplane is there are no smooth surface. I mean, it is one, it's just plane, it's just straight, right? At any axis, at an axis that which you see, it's just straight. That's what a hyperplane is. There is no jagged or curvilinear feature of it. Okay. So it's a hyperplane, which is what we are fitting.
and here we are calling it as R square. It is actually regression square or something. What is it? It's an R square.
Yeah, R square. This to R square, VC told it's a measure of your degree of variance of your
Definition I understood. R square is a commonly
He
used.
wants to go to history.
No, not history. Okay, then I'll check.
R square tells
Not-
R square.
Sorry, sir, not history. I'm saying it's MSc is actually I understand. No? Mean square
MSc is
error.
an error metric. R square
Yes, sir.
R square is more a measure of goodness of fit. How good, it's a measure of goodness of it. It's the other way. While I'm erroring, R square, MSc tells that am I hitting my objective function? On the other hand, on my loss. On the other hand, what am I trying to do? I'm trying to build a linear regression. How good is my model? Which is what R square tells me. Like, is my hyperplane good or not? And R square closer to 1 is good, R square closer to 0 is bad. Okay. Okay.
So
You have to.
yeah, I'm sharing. Yeah. So that's it. Like, so I went on predicting how the model performed. Like, I gave the exact same data point of the first one, but the loan amount should be around 5,000, but here it predicted around 6,983. So this is for one hot encoding, and then I did the label encoding here. So it's generally the same, and except that as we discussed, like the grades are encoded into 1, 2, 3, and ownership as this one. So this is my linear regression homework that I did last 2
And
days.
did it make any difference? I'm just curious.
No, yeah, actually, like the mean square error was the same. Like it was around 0.85, and R squared was 0.14. And I used the same data points here too, but then it gave me a different value around
Okay. All right.
7,000. Yeah, so it's quite just like I think 100 points below 100 points difference. Yeah, and this is without standardization. So
Yeah,
as we
that's the
discussed,
one
yeah,
where
this
we
was
had the
but
crazy
here to
MSc, right?
yeah, and here to the R square was 0.15.
Hmm.
So yeah, that's it. So can we move to the image classification?
Yeah, sure.
Shall I share that?
Just as a heads up, we won't have any discussion on image classification today. We'll just see what's done. We'll take up the discussion in next class. Want to cover other topics today.
Shall I go ahead, or shall I stop
No,
now?
you just walk through, but we won't do any question answer here.
Yeah, sure. So I'll just show you the output of this model first. So here is where it happens. Yeah. So these are the test images that I had. And for the image only with this Italy, it was good, and for dosa it was good, and for vada it was good. But when I gave the images that had dosa, Italy, and all these combined, it just predicted one. It was obvious, but I'm not sure on what basis it took Italy here, or on what basis it took it predicted vada here. Or yeah, that was quite interesting. And let me share you. So which image shall I give? This this vada image shall I give here? I'll just go ahead with. So it predicted the class correctly.
Okay.
So this is the output, and now to walk through the code, there was two parts that I was able to observe here. First one is to build the model using Torch, PyTorch, and first what it does is the image folder, whatever the images are in the image folder, it resizes it and it normalizes it, and using this piece of code. And then one thing that was particular was like the folder structure, how we are placing the image. So as we can see here, the image has to be placed in this folder like data, and within the data folder we have train set and the validation set here. And in the train set we place it in three different folders, which one folder which has only Italy images, one with dosa, and one with vada. So what it basically does, it picks it assigns all the images with this name. So that's why in the last model class prediction we could see it said that train vada as an output. So this is one important part here that I learned, like how we are placing the images in the data structure is into the folder is important. And then the data is loaded here loaded, and then we perform the ResNet. This is like a convolutional neural network. So I think Bhargav, like I think we need a deep understanding about what these means here.
Yeah, we'll do all of it.
Yeah. And then so here the feature, like there were as we had only three classes, we just gave three. And if there are like four, if we are going to add some other like biryani or something, like I think we have to add four number here. And then so this was like till building the model, and now we are training the model. I just did it for two iterations, two epoch values, and it took me around 11 minutes for this data set. And the training accuracy was 64 and the validation was 83, and for the second iteration it was 82 and 95. It has really improved. And then we went ahead and saved the model. And now this is where we actually predict the values using this model, like predict the image. We are again we are calling this model where we have saved it. And then the test image that I showed you, right, like so that is being pre-processed into the same 24 224 by 224 pixels, and it's been normalized. And then we are and then we predict it using the model here. So this is how so the first part was to build and train the model, and the second was to test how it predicts the images.
Understood. Did you use a GPU? Or did you use only a CPU for training?
No, only the CPU.
Okay, the reason I asked all of you to use Collab is you can do TPU on the runtime. If you can go and then just go to the runtime, please. and then change runtime type.
Runtime type.
Where is it? Change the runtime. Okay.
Runtime type,
Okay.
and then you can
Oh,
select.
right.
You can select a GPU. Okay.
Okay.
So when you're running, please use a GPU to do that.
Mhm.
It'll help you
So,
run faster. You can do more epochs and it'll be faster.
all right.
Okay.
Yep.
It has, I mean, I think it will get cut off after 4 hours or 8 hours of training, but for our problem, you're telling it took 11 minutes, like this would have been done within a minute in GPU. And in 10 minutes, you could have run for many more epochs, right? When you have more data, that's something that you will do. I have a bunch of questions, but I'll probably post it, I'll ask on the group later today or tomorrow. But this is good. Thanks, Vidya. We'll start with,
Hey,
so
just have one question. How much of this code was provided by GPT and how much was it written?
What is that? Like,
how many, like, did you generate the entire thing using ChatGPT or you Googled? How
yeah,
did
yeah.
you do the code?
No, the entire thing was generated by ChatGPT. I didn't have any clue on this, and I just the most part was the time it took was to download the images and to select the proper image without, like, the Google had many images which had mixed with mixed categories. So one thing was to filter out the exact images, and the other thing, this code was like around, it just took 30 minutes using the GPT.
Okay. I mean, so I know there's a group that's working on it. Is it all of you working on the same code and same data? You're all having your own versions of the data? Vijay?
Uh,
I mean, each one has a bunch of files on their GitHub.
Mhm.
So we generally ask them to download and then, collate them before running the algorithm.
Okay. What's the validation process to ensure that the data
That's,
is correct?
that's nothing.
Okay. Okay. So no one is looking into it to check if a dosa has only dosa and not.
No, nobody. I mean, if at all, just eyeballing, I suppose.
oh, like you say, the images that we downloaded, Bhargav, which one are you saying?
Yeah, correct.
Yeah, I went through each and every image.
How much
and
data points did you use to build the model?
I was able to get 216 for training, and around 74 for, around 54 for validation. So
Okay.
it was total of 270
Okay. So your
in
model
each category.
so
In each category.
your model had an accuracy of 82%.
Yeah.
With 216 images. So one number of images you used is too less.
Mhm.
And the accuracy is not a good metric. So both of it go and then figure out and optimize. Okay. I've given you another homework on specifically for you and everyone who's working on this particular problem. The question that Vidya asked was on the test, if I have both idli and vada, how is this getting done? So the thing to understand is there are ways to visualize the neural network itself, the model that's been built. The most common one is called GradCam. So we'll cover what GradCam is a few weeks from now, but write the code and then show the output of it on Monday. Okay. Okay. Like, is it okay if we go on for another hour or so? Does anyone have a hard stop? Vijay have some yoga class morning.
That's okay, but we can go for an hour. I don't have a problem.
Yeah, well.
Others, do you have an exam? The students tomorrow? Does anyone? All right.
Okay, then.
All right. Okay, then it's fine.
Start a new. We'll start with logistic regression. We'll talk about, and then we'll start talking about how to do evaluation metrics. This session will be entirely led by Naveen. Validation metrics, I'll come to it, but entire logistic regression in its full glory and gory details, Naveen will do. Over to you, Naveen. I'll be off video for some time.
Hello. Yeah. So I'll be taking up logistic regression, like completely not from a mathematics point of view. From morning, I was trying to derive all the equation. At last, I was able to achieve, but like I'm not confident to bring it here and explain it, break it down into pieces. So maybe we'll take, like, if we want to derive it, we'll take it up in a different call, okay, with a different set of people who all wants it. But for here, what I'll do, I'll just show you what is the intuition behind logistic regression, why actually we need logistic regression, why not linear regression, and how can we evaluate, and what is the baseline of improving it. I just have few slides stolen from some YouTube videos. Yeah. Is my screen visible?
Yes, it is.
Okay. So I'll start with linear regression. Let's say we have a data set. I think Troll 2 is a movie. The basic is based on how much a popcorn consider I am watching a movie. So I have a basket of popcorn, okay, and it is weighted. So the ideology behind this model is if you eat more popcorn, you will love this movie. If you eat less popcorn, you will not love this movie. So that is the analogy behind it. So why linear regression cannot handle this? Obviously, it is a classification model. So it values cannot be continuous. It should be discrete. It should be either he loves troll 2 or he doesn't love troll 2. It cannot be like 0.7% he loves troll 2. It cannot be like that. So in like only based on this reason, we are introducing a new model called logistic regression. Logistic regression is nothing but it is similar to linear regression, but the output will be either 0 or 1. Okay. Now, anyone have heard of a function called sigmoid?
Yeah.
Anyone aware of sigmoid function?
Yeah, I've heard of it.
Not you, Bhargav.
Sigmoid, is that the one that's
When it is less than
between 0 and then curves up and then goes to 1? Is that the one?
Yeah.
Right?
Yeah, 1 by
exactly.
plus e power.
Yeah, 1 by 1 plus e power minus y or something like that, right?
Oh, wow. Okay. Yeah, exactly. That's a formula for it. Okay.
Right. Okay.
So here we are going to use a sigmoid function for this particular problem. So the reason why again, like if your data doesn't fit this, wait a minute. Yeah. So this is a sigmoid function. If your data doesn't fit this S-shaped curve, then you cannot use logistic regression. Okay. So if it fits this particular shape, then only then you can use logistic regression. The formula what we see told 1 divided by 1 plus e to the power minus x. Here x will be our input. Whatever, let's say here if it is
0. So Naveen, question. Correct me if I'm wrong. So this is a pretty unique thing in the sense that there is an element of classification ones and zeros, and yet this function is differentiable. Am I right?
Yes, it is differentiable on. I didn't get you.
No, if you look at this function, you can still differentiate the function, right? It's not discontinuous, right?
Yes. Yeah,
okay.
that is how you update the laws and like the gradient descent steps in here.
Okay, all right.
Okay, so yeah, so what we'll do is we'll try to fit this shaped line. Again, the thing is, right, so like how will we measure the error here? So let's take an example, the same thing, right? So you have a data point here, which is the red dot here. You'll straight away populate to this particular line. So if you see the difference between these two, it is huge, right? So like similar to linear regression, how do you fit like how do you find a sum of residual in linear regression? Is draw a line, draw a predictor line, from that point towards that particular line and find the difference between it. So that is how you calculate the sum of squared error in there. here, this sum of square error, the residual is replaced with a term called likelihood. Okay, so likelihood is nothing but there is a one niche difference between likelihood and probability. So what probability is, let's say you have given a function for a data point you're asking. Let's say this guy is 70% probably he's taller than the whole class. That is what probability is. Likelihood is you have, let's say, you have data points. You need to tell the function how much this is likely to be fit the data point. So to be, I know it is more confusing. To be in more easier way, let's say probability. Okay, I'll show this equation. This might be good. So let's take in normal distribution, the probability is nothing but which is the area under the curve. Let's say here our mean is 155.7 and our standard deviation is somewhere around 6.6, I guess. Yeah, this is two standard deviation. Then one standard deviation is around 6.6. So the area which it covers under this curve is called probability. So what we can say is, like easily we can say 95% of the population will fall under standard deviation. So that is what standard deviation here, like that is what probability here is. Likelihood is on top of this curve. Let's say if a student fall here, then we'll tell he's less likely to be taller. If it is exactly on the mean, he will be telling that he or she is more likely to be taller.
Isn't there a clear statistical definition for likelihood? I'm just thinking, because, or is it merely because the way you put it across, it sounds like
both are same.
No, but isn't there a very clear statistical definition for likelihood?
Bhargav, like, have you ever of any
likelihood functions? I kind of faintly remember from a previous life.
Yeah, it's just so it's just in some sense it's like the probability of the y-axis of that one particular point. That's it. That's it.
Even for continuous distributions, is it?
It's only for continuous distribution. I mean, in general, all of okay. So we haven't gone to discrete yet. Okay, so all to summarize what Naveen told, can you go back to the previous slide? So we talked about yeah, let's stay here for a minute. All we are doing is that our data can be dispersed in any range, right? But we are going to do a functional transformation into this particular form. So we're going to find like how we were doing line hyperplane. So we want to fit a line, right? Given my data in my linear regression, I want to fit a line. And the line is unbounded, right? On the other hand, I want to do only for classification problem. And classification problem, what is the problem? What is the challenge? My target variable is discrete. It's only 0 or 1. If it's binary classification, it can be 0, 1, 2, 3 if it's multi-class. But let's take binary classification. Like one that he showed here is binary class. I want to do it only 0 or 1. So like how I want to fit a line, here I want to fit this S-shaped curve. Why is it yes? Because there is a steep, like at the center, that's when I cross from being 0 to 1, it immediately ramps up. It is not going over, it's not a slow death, it's immediate, so that I know that I immediately convert, and most of my data points are either below 0.5 or above 0.5. And that, how is that S-shaped curve going to be fitted is what we are going to learn, right? Like the line itself is learned, here the S is being learned. The S has the amazing feature that the S will be very steep, closer to 0.5, and then the S will continue. That's the entire aspect of what we are trying to do. Does it make sense?
Right.
Okay, so still it's curve fitting. Like literally, the underlying thing that we are doing is, we know the curve, because that's the hypothesis that we are taking, is that it is an S-shaped curve called fitted by what is called a sigmoid function. And we are going to learn the parameters that will make this S-shaped curve.
And what is the, from a y-axis, if you're plotting it on the y-axis, what is the maximum value that it can take? It would that be
The y
1?
is bounded, no? Y is bounded. 0, 1. That's it.
Right. So, okay. So that's,
Okay.
and how do you convert your data into that bound?
I'll answer that. We see, just if you see here, when popcorn, there is some circles below, right? And then there are whatever that color is, I don't know the color, but on the top there are blue, right? 1, 2, 3, 4, 5 circles, and then bottom circles. That is how the data is. Given my data, and then I know that when I get less popcorn, I don't love. When I get more popcorn, I love. Now using just this data, can I build an S-shaped curve? Now your question is, how am I going to do that? Which is what the functional form that you told, right? That's called the logit. That's the logit function. That's the function that you're going to use to convert to fit the data.
So what you're saying is, if you love, it's 1. If you don't, it's 0, is it?
Correct. That's my target variable. And then there's popcorn. When I eat 1 popcorn, I'm a 0, put the round there. When I have 8, what is the value? I put it on the top. It is not put it on the top. I'll put it into the logistic function so that I know what my x-axis is. Right? My x-axis is my logit. My y-axis is either my 0 or 1. And then now I can go and learn it.
Okay.
Okay. No, you're not convinced. Okay. So let's understand, how did we learn linear regression?
No, I understand it intuitively, no doubt. So see, one thing I understand about this is, I mean, the beauty of something very beautiful about this function, which is the fact that it suddenly goes steep. So which means that the transition from 0 to 1 is very quick. There is a very little chance that something will be caught between 0 and 1. Is my interpretation correct?
That is correct. But
so that's one. And I think typically if you have to do that, you'll have to put a straight line and then another straight line and then another straight line, isn't it? It's like one straight line in the horizontal direction, then one vertical, and then another horizontal. That's how you would have to do it, which means the whole thing will be discontinuous, isn't it? You can't even differentiate that. This allows us to get close to such a function. Think of a step function. This is like a step function, it's just that it's differentiable, right?
Correct. Correct.
I can get all that, and I can also get that, it can help us to learn. Again, would it be just binary classification or anything more than that too?
Can you stop sharing? May I share my screen? Okay, let's understand this. Okay, now let me annotate here. Hopefully I can write. Why? No, man, let's suck at this. I have to do it. Okay. What did we do in y equal to a plus bx1 plus cx2? Let's assume that this is a model that we built. This is not what we'll do. We'll call it properly. W0 plus W1x1 plus W2x2. Right? This is what a linear regression is. We have some value. We already know what y is. We know what x1 is. We know what x2 is. In data, we are going to randomly initialize some value, and then that's how we're doing for every single value over here, right? So here, in the same way, if you see here, what we are going to do is that we are going to do one over e one. This is how it's going to look like. Okay. So I think I have to. It's going to look something like this. Okay.
Oh, so that's
literally function. For every value, I'm going to find this. Everything is known except W1 and W2. That is all that I'm going to do. Now, Y value is going to be either 0 or 1. For every value, I know if it's 0 or 1. I know what my x1, x2 are. I can go and build it.
and here x1 and x2 are of course the independent variables.
Correct.
Right? Oh,
Correct.
okay. So what we are saying is, given an independent variable, we are literally converting
We are doing this transformation. We are doing this functional transformation, which
to
is
a 0 or a 1 effectively, close to, right? Literally, right? It gets very close to that, right? Because if
correct.
it's very steep in between,
This function will be between 0 and 1. That's it. This function, like this particular function, will always be a value between 0 and 1.
right?
Correct?
Right, it would be correct.
I'm telling you, this function will be always for any value of W1 and W2. This function is always bounded between 0 and 1.
Again, I'm nitpicking here. So is that a minus and a bracket there, or?
Yeah, you're correct. Yeah, that is sloppy me. You're correct. Yeah, correct.
All right, so it's basically 1 by 1 plus e power minus x, correct, effectively, right?
For
Something like that.
We're going to do this. So now for every value that's there, now we know that for some, we know if it is for every y is 0 or 1, we have the value of this. Now we need to go and then figure out. So okay. So in linear regression, what we did all of this. We use some random value of W1, W2. We know we do for random value for W1, W2. We know what y hat is. Y hat will be a value between 0 and 1. I know this is my original y. For every value of it, I know my y hat. Here we used RMSE. I'm sorry, we did only mean square error, which is equal to y
minus y hat.
Y hat divided by n. Right? Remember, everyone on the same page? This is what we did.
Squared, right? Y hat squared.
Square. This is what we did. Mean square error. Same thing. We are doing, instead of the same thing, we are putting it into some logistic function so that this value, instead of being unbounded, is bound between 0 and 1. Here it is a curve fitting to a line. Here we are curve fitting to an S curve. That's it. Okay.
And what would be the error function here?
Now we will talk.
Okay. So we see this will be our error function. So it will be y log of p plus 1 minus y log of 1 minus p. So the reason is, for binary classification, y, which is the dependent variable, will be either 0 or 1. Okay. If it is like, what is log p? Maybe let's go here. For an example, this is 1 and this is 0. So let's take I'm plotting away, the popcorn is somewhere around here 10. When I go fit this, I can roughly call this as 0.98, right? So this y value will be around 0.98. So my probability of y will be 0.98. So that is what the probability is. When I do here, so like this is love troll 2. When I do this is does not love. So obviously the probability will be the whole probability will be 1 minus the probability of who does not love troll 2. So what we are going to do here is, for an example, let's say if some values that comes under love's troll 2, we are going to take the probability as it is. If something is 0, which means does not, the negative for class, what we are going to do here is we are going to like do 1 minus the probability of which does not love troll 2. So we are going to optimize this function for the minimum. Like let's say here the probability is huge, right? So if you compute here, so this is around 0.4. So the difference itself is huge, right? The difference 0.4, then the difference would be around 0. Sorry, this would be the difference would be ideally 0.6. So what we are going to do here based on this equation is, if let's say if my output variable is 1, then I'm going to take log of p. Why log is like it is on a continuous multiplication, right? So like when you do continuous multiplication of all the variable, it will end up in 0. So when you do log of each variable, again it comes under addition. So your like the loss value will be defined. So that is the reason why do we use log. And if the value is 0, then automatically this will turn on. It is like a switch value. If it is 1, then turn on this. If it is 0, then turn on this. Okay. So here the P is our predicted probability, what I've told you, like from x-axis, like where the curve touches on the y-axis. So that is our predicted probability. Again, here example, if y is equal to 1, then only this term will exist. When y is equal to 0, then only this term will exist. Yep. Question? Questions like?
So just repeating what Naveen told here. So we had mean square error. This is super important to know. This function is like the most commonly used function. So this is like, if you don't understand, please ask, because like for the rest of the whatever 2-3 months that we do, this function is all that we are going to use. This is important to know. The loss function for classification model is called cross entropy loss. Okay. And we'll start with the basic understanding. What is entropy? I can only ask VC. No, VC, what is entropy?
A measure of randomness.
A measure of chaos, right?
Chaos.
Yeah, measure of randomness, measure of chaos, right? So what happens is, let's say you put something, shake fully, and then leave it, it all is jumbled all over the place. So the measure of chaos, randomness that happens is what entropy is about, right? It's the same definition we are using. We are taking that concept from physics. It's one of the most fundamental concepts in physics. We're going to borrow that into definition, borrowing that into this field of machine learning, where I want to measure some degree of chaos, right? Now, entropy is a measure of chaos. So high entropy means there's high noise that is happening. Okay. What I want to do is I want to minimize that. Okay. My entropy loss, I will come to cross what it is. Entropy loss, I want to minimize. What is cross entropy loss, right? So this is like, if you go and see.
Question, sorry, if you don't mind. You say log there, is it to the base 2 or to the base 10?
You tell me.
Generally, entropy, if I'm right, is defined, at least in the information theory world, it's to the base 2, right?
No, it's all natural logarithm, not to base 2. It's log to the base.
P log P? Negative P log P? I thought it was always.
P log P is entropy. It's defined. It's ln always. Natural log. It's always defined to the E.
That's so. But I'll give an example. So when you toss a coin, and if the probability is 0.5, we say the entropy is 1 bit. right?
But yeah, correct. But here, because it's binary, so it doesn't matter. E and 2 will give you the same answer. How
Would
do you
it?
generalize it?
Would it? Because
I need to think.
if you think about it, negative P log P, if you toss a coin, then it's negative half log of half. If it's to the base 2, then you'll get 1 bit, right?
I have to check what my understand. Okay, I'll have to go back. It's been a while. My understanding is it's to natural logarithm. I'm quite confident it is definitely not binary to the base 2, but I will check and I'll get
Because
back.
if it's natural log, then usually we put it as ln, right? We don't put it as log usually.
Correct. That is true.
The nomenclature is ln, right? Anyways, we'll look into it. Probably I'm thinking of trivia here.
Okay. Okay. So what we're
In
doing?
most of the definition, it is ln. It is like logged in. In some places they've
logged
written.
in?
Yeah, it is logged in.
Is this logged in?
Yeah.
Really? Not natural logarithm.
Let's check. I mean, we'll dig a little
Okay.
deeper.
I haven't done this in like ages, so I'll learn something new. Good. Okay. So what it does, cross entropy, is that I'm going to find, okay. So there are two parts to it, y log p and 1 minus y log 1 minus p, right? So it tells that I'm going to take these two and then I'm going to minimize, take the subtraction of it. So it's minus, entropy is minus y log y. Okay, so so that's like, so I want to minimize this particular equation. What does this equation tell? It tells that when if y and log p are together, so for example, here y is the actual value, p is my prediction value. So if it's 1, 1, 1 minus y is when it is, so if it's 0, 0. So I want, when it's 1 and 1, I want, that is okay. Or if it's 0 and 0, it is okay. When they are opposite to each other, I want to minimize that particular loss. That's what this entropy does, right? This equation is trying to discriminate whenever I make a false prediction. Okay, you can try the easiest thing, I'll give it to you all as a homework, is that for value of y, different values of y, and for different values of p, and y and p, remember, is y can either only be 0 or 1. P is a value between 0 and 1. Remember that. Okay. For random value of 0 or 1, which is y, and value between 0 and 1 for p, figure out what this looks like. You will get an understanding of what is happening. So it's telling that when my things are so basically, if y and p are both 1, 1 or 0, 0, this entire equation becomes 0. I'm correct. When they are opposite, when they're not, at that point in time, there is high amount of chaos, and that is the chaos I want to minimize. So my equation will go, and that's why I will go use again gradient descent, and then I will go and then solve it. Remember, gradient descent is done on where? On which function? This is super important, keeps coming up again and again in machine learning. You should be very comfortable with.
Convex.
Parabola.
On the parabola, right? Sundar, in this, where is there a parabola here? Where is the parabola? Parabola was in linear regression. No, now we're in logistic regression. What's happening here? Everyone's gone silent.
I think I need to dig deeper. I couldn't get this.
No, the question is.
No. In general.
The point is your gradient descent. I'm descending on where my gradient. What should I take my derivative? Like where are my
So maybe
derivatives taken?
if you take first order derivative of that sigmoid equation, so you will end up something like I forgot, like you'll end up with two values. When you substitute values for it, the curve will be automatically convex. I've read it long back.
Okay. Understood. Okay. Okay. Someone will derive it. Okay, we'll do this as a separate session, but worth looking into it. Okay. Oh, you already have somebody sharing. This is awesome. When P and Y, there's a value, what happens? Good. That's what I was telling. Nice. Okay. Okay. We will go to the next aspect. Okay. Okay. I think it's now a good time for all of you to go brush up some math and learn a bit more about entropy, cross entropy, gradient descent, so that you understand and come back with more questions and have some better understanding so that we can have slightly deeper conversation. Otherwise, you all know it's 4 lines of code which ChatGPT will give you. Your differentiation will come and you can understand what happens under the hood for it to make sense. What is the next topic that I wanted to cover today? I wanted to go over data encoding. We went. I want to go over validation and classification metric. Classification metric, I'll cover next class because it's too late. It's too deep. I will cover the concept of validation. That's super important for us to know. I'm trying to figure out. Okay. I have. Okay. We have this. Vidya, where is Vidya? Hi, Vidya. You did train, test, validation, something and all. What does that mean?
Train is a train data. It is a data set for training the model and for testing how well the model is able to test the data set. So
I don't understand what that means, Vidya. Unless
no,
someone understood it, it's very hard. What does it mean? Training the data set, some data to train, I understand. But
yeah.
What does test mean? What does validation mean?
Yeah, so the model is actually evaluating how well it is able to predict based on the trained data set. So it means that it is actually comparing the values whether it has predicted right or wrong using the test data set. So the test will also have the entire, for example, if we take the loan data set that we were working, the test it was actually split into 80 and 20%, meaning that both the data set train and the test both had the values of default column in it. So while the data was training the model with the train split, that is 80%, and it compared the result of it using the test data set. For example, if for data point 1, if it predicted 0, it went and compared whether it was actually 0 in that or not. So how well so I that's what I understood.
Why do we want to do that?
To understand how the model is actually performing. So that's how we went ahead and we calculated the classification, the recall value, precision value, and all, right?
Recall it. We'll just stick to, there is some metric that we want to understand. Let's understand it, whatever we have right now, mean square error, right? We want to understand how well the model performed. So we want to do test, right?
Yes.
Okay. Is there any other way? Like what? Like, is there any other way we can do this apart from this? Like an 80-20 split?
Any other way? Not sure. The val for which you're asking, Bhargav, like after the prediction?
Yeah, you built a model, you have some data, you
Yeah.
built a training model,
Uh,
and then you're trying to evaluate how good the model is.
mm,
And that's why you're telling that I will need a test data set to know. If I
mm.
have no test data set, what else can I do? Like, why do I even want to know that? You give me data, I give you a model because I believe in the power of gradient descent. Why do I even want to know this?
Yes.
Because the data is a sample, right? It's not the entire.
Okay. So,
So the model that I'm using could be, I mean, it could pick up a lot of noise in the data because
okay,
data will have a
point.
lot of noise.
Fair point.
So I might overtrain the model given the data, for instance, because it's a sample.
Fair
So let's
point.
say I'm looking at a freak. Let's say hypothetically, I pick some data from a population and it just so turns out that this data is freak data. I wouldn't even know that, right?
Okay. But how will 80-20 solve it for you, VC?
No,
Because freak data,
80-20 may not solve everything, but ideally not 80-20. See, I think the ideal thing to do is even the 80-20, I would want to randomize it, right? That's the best way to do it.
it's a randomized 80-20, no? I'm randomized 80, I get randomized 20.
Again, okay, you can do that, but then you can pick. Say, let's say you have, just thinking, let's say you have 10 data points and I want to train on 8 and then validate on 2, hypothetically, okay? But the question is, how do I pick the 8?
No, but why do you want to do that? Which is, I have my data, I give you a model. What is, I don't understand. What is meant by,
So,
what is meant by,
let's say,
No,
Bhargav,
see, the model
Bhargav,
is,
Bhargav.
sorry, go ahead, Arun.
Yeah. So I think he is trying to understand what is validation, why we need validation,
right,
why
because
we
I'm
are
giving
No,
you
why we are
because,
data already. I'm giving
why
you
we are
data
actually
already.
building the model. See, we need to
It
do
is
we are starting everything for a purpose, right? So
everything from?
we do all these things for a purpose. There is a business problem we are trying to solve or something like that. And this validation is actually tells me saying like whether the particular problem is solved or not using this particular. So,
Or else can we put it in another way, like we can it is used to evaluate the performance between the different models. So if this model is not
You're
performing
telling
well,
I
we
have
can.
competitors, so I have competitors. I want to find a way to figure out from my competitors which one to pick, right?
Yeah.
But I'm telling you, like, let's say in linear regression, I already have a linear regression. I have an MSC when I train the model. Like the model already gives me MSC. Why do I need to do another validation and then find an MSC? You see my problem. If I'm
Bhargav,
getting the
no,
same
but in reality, I might I might hit some data which doesn't really fit into the data set that I use for the training, right? So how do I even know that?
come again?
Bhargav,
No, I
uh,
might get some data which are, I mean, again, the model is finally based on the training data set, right? So
I think it's to understand the learning pattern, right? So if there is a particular data points, the model need not to learn the hypothesis behind it. It may memorize it, or it may understand with a different hypothesis. Let's say for one particular pattern, there are a lot of ways of solving it. One, I can find a ideal solution for it, or else I can just memorize it and I can do it. To understand whether my model memorizes or not, whether the pattern identification is similar to the external world or not.
Right. When I was young, I was good at it. I can mug anything and get good marks. So yes, correct. So yes, that is correct. Okay. So this concept, what Naveen, I'll explain again, but what Naveen explained, that concept is called generalization. There is a very specific term that you should all know. It's called generalization. I build model on like Vijay started correctly. Naveen's explanation is just bang on. What it tells is that I only have a sample of my data. It's not true representative of it. Unfortunately, I cannot go and then sample anything more. It's a sample that's there. Now, I want to understand that did the model really learn anything or did it memorize and then do something? Can it generalize in the wild? Like, can you give me the confidence that when I put this model in real life production setting, so if you use everything only on my, if I report an mean square or whatever metric that is on my training data set, it is called in sample. It is all built on the sample on which the model is built. And unfortunately, because of the complexity of my algorithm, the hypothesis that we're using, it is complex. It can go and memorize and it can overfit. We'll talk what overfitting is in next session. But it can go overfitting really means that I can go memorize everything. Like me in 12th standard, I can memorize everything. I used not anymore, but back in the day, right? So we now want to evaluate if it has memorized or if it's really generalizing well in a new setup. To do that, one of the ways people can do is I can go put it in production and then I can evaluate and see. Unfortunately, that's a very expensive process because if the model is wrong and my business process is getting messed up. So I want to have a way where with the data itself, the data that I have, can I efficiently figure out what is the right way to use, right? That's the entire value, that's the entire concept. So to do that, given my data, I split data into two parts. One data I call train, other part I call it test, validation, whatever you want to call. Then I will go and then build on training data set and I can build my test data set on my test. And I want to ensure that the MSC, whatever metric, it's precision recall MSC, whatever metric that we are looking at. For example, now we know MSC, we'll stick to that. The MSC I get in my training set is the same as my MSC in my test set. If these two are kind of similar, I know that the model generalizes well. If my MSC on my model is very low and the MSC on my test data set is very high, it means that my model has memorized a lot. You will never have a situation where MSC of your training data set is high and the MSC on your test data set is low. That's freak, right? Now there can be an one of the times it could happen, what VC told is that I'm going to do this, say 80-20. This 80-20 is freak. My model is awesome, but because it is freak, it is giving very high error for my MSC. How do I solve this problem? I did 80-20. 80-20, but I'm telling you the model is awesome, but my random number 20 that I took was like freak output. And that is messing up my model. And I didn't know that.
Mix and match the 80-20. I mean, it's like.
So the game is that now.
Is that K fold or something like that, right? They call it that way?
Exactly, correct. Now, what you're going to do is that I am going to, so in something like this is what you're going to do. I'm going to build on 80% of my data and I'm going to do 20% on test. That's one model. I'm going to repeat this process 5 times. This 20 is going to keep sliding down. So I'm going to use a different 20% every time. That way in 5-fold, it means that every data point has an option to be both in the training set as well as the test set. And then I'm going to get what the error on each one of it is. And then I'm going to take an average of it, which is called my K-fold cross validation. This is a common concept. which is what, like, she used validation also in Vidya's demonstration. So that's what it is, right? So that's pretty much what validation is about. Validation is, I need to understand how what generalization looks like, and to generalization, I do this process where it's expensive in production. I want to do, and then the other point which one of you told is that if I have competing models, I will pick the one that has the lowest cross-validation error. Okay, that's it. It's pretty much all. Like any model that you select, like deep learning, standard machine learning, doesn't matter. These are all like literally two fundamental concepts. Every single model, the loss function is cross entropy loss. Classification model is what drives most of what we'll ever do in this course. And in general, in application of machine learning also, like a lot of the problems are just classification problems. So that's one. The second thing that we learned is that validation happens because we want to understand generalization error, and we want to do k-fold cross-validation to do it. So if you have 10 million data points, you don't need to do k-fold cross-validation. It's like law of large numbers. You know that even if you do 80-20, it's 8 million, 2 million. That's a lot of data points to get it. Typically, you do k-fold cross-validation when your data size is between 10,000 to 100,000 data points, because at that time you can have this freak accidents happen. When you have large data points, the larger you get, you can build only one model and you should fairly be fine. Okay, so we've covered this. Any questions?
Bhargav, so
Understand the
that's
sequence?
yeah, the CV equal to 5 during the cross validation, right? So that is the standard that it takes.
Yeah, just a rule of thumb to do 5. The thing is, like 5 should be good enough. From 5 to 10, the value won't change much. Like you can keep doing. The extreme thing is leave one out. You build a model with everything except one. It's called leave one out, right? So you can keep doing it, but when you have a reasonably large data set, say 100,000 data points, 5-fold should be good enough. Sometimes you would do 10-fold, but remember that if your cross-validation number is high, it takes you longer to train. So the model takes longer, right? So it depends on how much time you have, but 5 should be good enough.
Oh, thank you.
So it's like so when we train, we are actually taking 80% of the data, train it. So the output of that is actually, so let's take it as a linear equation. We get linear equation. So y is equal to mx plus c. So I actually get 2 bits. So now when I'm going to validate or test, I'm going to take the same equation. I'm just going to put some x values, x values with the same m and c which I've already identified in the training, and then see like what is happening, and then I actually compare that with the actual values and see what is the difference, and then calculate MSC for that.
Correct. That is correct.
So
bang on. Okay, we'll stop sharing. Stop recording.
Yep, sure. Stop record.